Hey guys, Charles' law has to do with the relationship between temperature and volume. So it's the reason that on a cold day, your tires in your car might look a little on the flat side, and on a hot day, they're going to seem kind of full. We're going to play around with it. We'll pretend that we're taking a balloon here and sticking it in a freezer or an ice bath or something like that. So the equation is going to be V1 over T1 equals V2 over T2. I've already gone over that a little bit, so I'm not going to go into that. If you've missed it, go back and watch some of my examples. I'm just going to give you a couple of problems that you can deal with and submit your answers. So here we go. The volume of the balloon that is at room temperature is going to be, it's going to be 5 liters, okay? And we're going to put that at 25 degrees Celsius. All right. So we want to know how big a balloon would be if you threw it in an ice bath. So what's it going to be like if you throw it in 5-degree temperatures? Okay. So that's a Charles' law problem. How many liters is my balloon going to be if I throw it in 5 degrees? So that's going to be, submit that under Charles' law number 1. And then I'm going to give you a problem on pascals, and you can submit your answer on that one, okay? So pause it if you need some time to do that math. Tell me how big that balloon would be, okay, if you threw it in an ice bath. So for example, just to kind of review in case my writing's a little bit muddled up, if you have a balloon that's 5 liters and that balloon is sitting at 25 degrees Celsius and you throw it into an ice bath, it's going to get smaller. Okay, if you're doing your math correctly, it's going to get smaller. 5 degrees Celsius. Okay, so I want to know how much smaller. So that's your Charles' law problem. Go back and review Charles' law. I gave you some examples earlier in the unit. Okay, now this one, you've got a muscle guy, and he's pushing hard down. He's got big muscles, big muscly guy, and he's pushing down hard on a piston full of hydraulic oil. That piston is connected through a pipe to a bigger piston that just happens to have an elephant on it. Of course, I think we've all seen this circumstance 100 times before. If I had $1 for every time I've seen that. Big old elephant sitting on a hydraulic lift. Okay, this is full of hydraulic fluid. So it's all connected. So when he pushes down, we want to know how much force he can generate, okay? So he's pushing down on this with 75 newtons of force. And this is 0.5 meters squared. That's the area. 0.5 meters squared, okay? This big wide platform here is 4 meters squared. I want to know how much force you can generate. It's pushing down with 75 newtons, so you're going to have to use Pascal's principle. There's some examples in the chapter prior. See if you can figure that answer out and tell me what it is. How many newtons of lift does he create by pushing down on that piston? Okay. 75 newtons push down on 0.5 meters squared of area. And that's a 4 meter squared area platform. How many newtons does he generate as he's lifting it? Okay. Remember, guys, Here's the math we're doing. 6 over 1 equals, or excuse me, yeah, 6 over 1 equals 12 over something. Okay, or sometimes I'll throw this problem at you. 6 over 1 equals something over 2. So the same way that you would do that problem is the same way that you would do those two problems, Charles' law and Pascal's principle. Give me your answers, submit them online.